All right, let's jump right in to the world of matrix and vector calculus. We're going to be looking at some of Professor Wu's lectures from Northeastern University, and this stuff's like essential for understanding how machine learning really ticks, especially with models like ChatGPT.
Yeah, these tools might seem a little abstract at first, but they're really the foundation for a lot of the most exciting advancements in AI.
And we're going to make sure it all makes sense.
Okay.
So why are matrices and vectors so important in machine learning?
Well, imagine, you're trying to analyze data, and it's got hundreds or thousands or even millions of variables. Trying to write out equations for all that would be, well, a nightmare. So that's where matrices and vectors come in. They're a powerful way to organize and manipulate data, huge amounts of data.
So it's like a really efficient filing system for all that data.
Exactly. Matrices and vectors, they let us compress these huge equations into something that's much more manageable. And it's not just about simplifying how it looks, it actually makes complex calculations possible and efficient.
That makes sense. Now, how does this compression actually work?
Well, think about it this way. Instead of writing out every single variable individually, we can group them together into these vectors and matrices, and then we can do operations on those vectors and matrices, which is kind of like doing a calculation on all those variables at once.
Oh, so we're not just simplifying the notation, we're actually able to manipulate the data in a more efficient way because of this representation.
Exactly. And this efficiency is really crucial for training those machine learning models. They often involve these massive data sets. Now let's bring in some calculus here. See how these ideas connect. Remember derivatives. They tell us how a function changes as its input changes.
Yeah, I remember vaguely derivatives.
Yeah.
But things get a bit trickier when we have multiple variables.
Right, absolutely. With multiple variables, instead of just getting a single number for the derivative, you get a vector of derivatives. Each element in that vector tells us how the function changes with respect to one specific variable.
So it's like having a multi-dimensional view of how the function is changing.
Exactly. And this understanding of multivariable derivatives, it's really fundamental for optimizing machine learning models.
Okay, so let's get to a specific example that Professor Wu mentioned, the ReLU function, pronounced ReLU, which is really important in neural networks.
Yeah, the ReLU function, it's like a switch. It turns on when the input is positive, and it stays off when the input is negative. It's a really simple behavior, but it makes it super powerful in the context of neural networks.
How so? What makes it so useful?
Well, this on or off behavior introduces this nonlinearity into the network, and that allows it to learn these complex patterns that wouldn't be possible with just linear functions. And to train these networks effectively, we need to understand the derivative of the ReLU function.
So how does the derivative of the ReLU function work? I mean, it sounds a bit tricky to figure out the derivative of something that's like an on-off switch.
Yeah, that's where the indicator function comes in. It's like a mathematical signal that outputs a 1 if a condition is met and a 0 otherwise. And it perfectly captures the behavior of the ReLU function's derivative.
Interesting. So the indicator function helps us to define the derivative of the ReLU function, which then in turn helps us to train neural networks. Now, what about those L1 and L2 norms you mentioned earlier? I remember those from linear algebra, but what about their derivatives?
Yeah, you're right. The L1 and L2 norms themselves aren't new, but their derivatives, they have some really interesting properties, and they're especially relevant to machine learning. For example, the L1 norms derivative, it uses something called the sign function, and this function basically tells us whether a number is positive or negative.
And why is that important? How does that tie into machine learning?
Well, the L1 norm, it's often used in what are called regularization techniques. And these are methods for preventing overfitting in machine learning models. By understanding the derivative of the L1 norm, we can see how this regularization affects the model's parameters during training.
So it's like we have fine-grained control over how the model learns.
Exactly. It allows us to guide the learning process in a way that prevents the model from becoming too specialized to the training data. That ensures that it can generalize well to new unseen data.
Fascinating. It's amazing how all these mathematical concepts have such a direct impact on building these AI systems that are robust.
Yeah, it really is. And speaking of building AI systems, let's talk about a really key concept called MLE objectives, or maximum likelihood estimation objectives. They're like the guiding principles behind a lot of machine learning algorithms.
Okay, so what are MLE objectives and how do they help us build better models?
Well, in essence, MLE objectives help us find the best set of parameters for a model. And we do this by maximizing the likelihood of observing the actual data given those parameters. It's kind of like finding the most plausible explanation for the data that we have.
So it's like fitting the model to the data in the most likely way.
Exactly. And to do this, we often need to understand the derivative of that MLE objective. By finding the derivative, we can see how tweaking each parameter affects the likelihood of observing the data. And that guides us towards the best parameters, the optimal set that best explains the data.
Makes a lot of sense.
Yeah.
So by understanding these derivatives, we can basically fine-tune our models to make the most accurate predictions possible.
Precisely. And this fine-tuning process, it's a crucial part of building effective machine learning models. Now that we know why these tools are important, let's get into how we actually use them to analyze machine learning models.
Yeah, we've talked about what and why. I'm curious about the how now. How do we calculate these complex derivatives when our equations are all matrices and vectors? I mean, they can look pretty intimidating.
They can be complex, yeah. But we can actually use the same principles we've been talking about, this compression, simplification. Instead of trying to tackle this massive equation all at once, we can break it down into smaller, more manageable pieces.
Okay, so kind of like divide and conquer.
Exactly. One common approach is to actually expand the matrix and vector notation into a more familiar algebraic form. This allows us to see each individual term and really understand how it contributes to the derivative.
Ah, so it's like taking apart this complex machine and seeing how each little part works.
That's a great way to put it. And once we've done that, we've expanded the notation. We can take the derivative with respect to each variable, just like we would in basic calculus. And then after we've calculated all those partial derivatives, we can put them all back together, assemble them back into a vector or a matrix, and that gives us the complete derivative.
So it's a step-by-step process of breaking down, analyzing, and then putting it all back together.
Exactly. And sometimes when we do this, we find these really interesting patterns emerge. For example, the derivative of a linear function, something very common in machine learning, it turns out to just be the original vector that was multiplying the input vector.
Wow, that's surprisingly elegant. So the derivative, in a way, it's kind of like revealing a hidden structure within the function.
Exactly. And these patterns can be incredibly useful. Once we've identified them, we can use them as shortcuts for future calculations. Saves us a lot of time and effort.
It's like learning a secret code to unlock these derivatives.
Yeah, and let's go one step further. Let's consider a slightly more complex example, a quadratic function. Its derivative also follows a specific pattern, one that involves the original matrix and its transpose.
Now, when you say transpose, you're talking about flipping the matrix over its diagonal, right? It's like a mirror image.
That's right. And in some cases, if the original matrix is symmetrical, meaning it's identical to its transpose, then the derivative actually simplifies even further.
So symmetry seems to be important here in simplifying these calculations. Is that a common theme in machine learning?
It is. Symmetry pops up a lot in real-world problems, and it can really make our analysis a lot simpler. For instance, certain types of neural networks, they actually have symmetrical structures, which makes their derivatives much easier to work with.
So by recognizing these patterns, these symmetries, we can really streamline the process of working with all these derivatives.
Exactly. And that brings us to a really fascinating concept called the trace of a matrix.
Okay, trace, like a footprint in the mathematical sand. What does that mean?
That's a good way to think about it. The trace of a square matrix is simply the sum of all the elements along that main diagonal, that line running from the top left corner to the bottom right corner.
We're focusing on that one specific line of numbers. What's so special about it?
The trace actually has some remarkable properties that make it super useful in matrix calculus. For example, the derivative of a certain type of quadratic form, one that involves a matrix, a vector, and its transpose, it turns out to be just the original matrix.
So the trace is like a hidden gem. That pops out when we take the derivative.
Exactly. Another really incredible property of the trace is that it's what we call rotation invariant. This means even if we rotate the matrix, the trace stays the same.
Wait, really? That sounds almost magical. What's the significance of that in machine learning?
It means the trace is capturing something really fundamental about the matrix, something that doesn't change even when we look at it from different perspectives. This invariance is a really powerful concept in linear algebra, in geometry. And it has tons of applications in things like computer vision and robotics, where rotations are super common.
It's incredible how these, abstract concepts have such a direct impact on the real world.
Hmm.
I'm really starting to see now how all these pieces fit together, these derivatives, these matrices, these traces. It's the foundation for all these advanced machine learning techniques.
You got it. It's those connections that make these concepts so powerful. By understanding them, we can move between different representations and perspectives seamlessly and gain a deeper understanding of these complex problems. And remember, all these techniques are being used to build those models you mentioned earlier, like ChatGPT.
So it's amazing to see how these pieces fit together. We've talked about derivatives, matrices, traces, but how does all this stuff actually come to life in like a real machine learning model?
Let's take a look at linear regression. It's kind of a classic algorithm used for predicting a continuous output, like predicting house prices or stock values. Basically, linear regression tries to find the best fitting straight line through a set of data points.
Oh yeah, I remember that from intro stats. But where do matrices and calculus fit into all of this?
Well, the best line, it's determined by finding what we call the optimal values for the model's parameters. These are kind of like the knobs and dials that control the line's slope and its position. And guess what? Finding those optimal values, it involves minimizing a special function. It's called the linear regression objective, and this measures how well the line fits the data.
So the objective function tells us how far off our predictions are from the real data.
Exactly. The smaller that function's value is, the better our model fits the data. And to minimize this function, we need its derivative, just like we've been talking about. By calculating the derivative of that objective function with respect to each parameter, we can see how tweaking each parameter affects the model's accuracy.
Okay, I'm seeing how this all comes together. So we use derivatives to guide us toward the best values for the parameters.
Exactly. And this process is actually automated. We use these clever optimization algorithms that iteratively adjust the parameters in the direction that minimizes that objective function.
So it's like we've got a self-driving car for our model's parameters, steering them towards the best performance. Now, can you remind me how the indicator function fits into all this? We talked about it earlier with the ReLU function.
You got it. The indicator function, with its simple on-off behavior, it's key to understanding the derivative of the ReLU function, which, as we discussed, is a fundamental piece of many neural networks. This derivative, defined using the indicator function, it essentially tells the network whether to activate a particular neuron or not during training.
Ah, so the indicator function acts like a gatekeeper for information flow in the network.
Exactly. And this selective activation, it allows neural networks to learn these really complex, nonlinear relationships within data. This makes them super powerful for tasks like image recognition, natural language processing, things like that.
Now, what about those MLE objectives, maximum likelihood estimation objectives? Professor Wu really seemed to emphasize how important these are. How do they help us build better machine learning models?
MLE objectives, they're really a core principle behind a lot of algorithms. They provide a framework for finding the best parameters for a model by maximizing the likelihood of observing the actual data given those parameters. Think of it like this. Imagine flipping a coin 10 times and you get 7 heads. An MLE objective would guide us to a model that predicts a slightly higher probability of getting heads than tails, because that's the most likely explanation for the data we observed.
So it's like finding the model that best explains the world as we see it.
Exactly. And remember, these MLE objectives, they can get pretty complex. They can involve these really tricky mathematical expressions, but that's where all the tools we've been discussing come in. Matrix and vector calculus, derivatives, indicator functions, all of that. It allows us to analyze these objectives, understand how they work, and optimize them to create these really powerful AI systems.
Professor Wu's lectures have given us a great foundation in the world of matrix and vector calculus. It's really fascinating to see how all these concepts are the building blocks of modern machine learning. Thanks for taking us on this deep dive.
It's been my pleasure. It's always exciting to see these concepts in action and how they're being used to build these really impactful applications.